forces. Okay? And the whole point of these forces is trying to apply them out to a variety of different physical properties. So how do we observe the world around us? Your textbook goes into detail about a lot of these. Ultimately, the ones that you're responsible for are those three. Okay? Your phase transitions, vapor pressure, and solubility. Okay? And so we'll look at those. The first thing I want to do is take a look at phase transitions. What would be a phase transition?
Like from solid to aqueous.
Okay. Solid to aqueous could work. Okay. I'm going to argue that solid to aqueous is a phase transition, but when we say phase transitions, we aren't talking about solid to aqueous. Okay. And it's not obvious in the statement, so I'm not saying you're wrong. Okay. But the solid to aqueous is involving how many substances? More than one. We're talking about whatever our solute is and water. So we're saying, does the compound interact with water? That kind of sounds a lot like solubility, the ability to dissolve in water. So that's still a phase transition. It is still dependent on our intermolecular forces, but that as a phase transition is typically classified under solubility, not under our phase transitions. Okay, so what's another option?
Solid to liquid.
Okay, solid to liquid. In this case, we're maintaining the same substance, okay? So we don't have to worry about a secondary thing affecting this. So when we go from a solid to liquid, what is happening?
We're melting it, or it's
Okay.
melting point.
So we could reference the name of it. This is known as a melting point. Okay? If we looked at a diagram, we've got a solid, roughly, and then going to a liquid. Of course, it turns blue. No, that was a joke. Okay? What's the difference between those?
They're more spaced.
There's a little bit more space. It's a little bit more irregular in the form of a liquid. Okay? So why does the solid have less space? Are we changing the volume?
It's more dense.
Okay? There is a density change. How much is that density change from solid to liquid? Pulling back way back at the beginning of Unit 3, supposed to be the end of Unit 2. Talked about densities. What was the difference in densities between solids and liquids? It's okay. The difference between solids and liquids, very small difference in densities. Okay? Their densities were almost identical. So there is a subtle difference there, but it's not a big one. Okay? So when we look at the volume change, yes, there's a volume change, but it's very, very subtle. Okay? So for the most part, we don't see a change in volume. So then why are the particles allowed to move more?
Because they're not, they're free to move a little bit more, because it's not one-to-one specific, volume set.
Yeah, but the volume is still kind of there. We're still locked in at that same volume. Why can they move more?
There's more space between. It's not structured.
The more space in between, again, goes back to the volume. Yes, there's a little bit more space, but it's not significant. So the volume argument doesn't tie in here. So what is the difference between the solid and the liquid if it's not a volume issue?
Some solids are loosened. They can move faster.
They can move faster. What prevents them from moving? Well, an attraction between molecules. The stronger that attraction is, the more likely they're locked in place and they would stay a solid. The weaker that interaction is, the more likely they can move around. So when we transition from the solid to liquid by adding heat, what are we doing? We're adding enough energy in that what happens to the attractive force between molecules? It breaks. Because that force is now broken, there's nothing locking them in place, and so what do? They move. Right? Kind of like if we put handcuffs on each of you next to each other, you're going to maintain a certain shape, right? Because you're now handcuffed to each other. If we remove those handcuffs, you now have a little bit more flexibility to move around. Okay? You're still confined, though, right now. right? Why are you confined? You're in a classroom, right? What happens at 9:45? You get to leave, okay? And we've removed that extra constraint. So when we're moving from solids to liquids to gases, there's a constraint that holds them in each of those locations. The solid to liquid constraint is the attraction between those molecules. What do we call that attraction? Right? We could call it a force. We could also call it a bond. Okay? How would we decide what that attraction was, whether it was a force or a bond?
What says a bond is within one molecule, the force is between multiple molecules.
Okay, so bonds are one molecule, forces are multiple molecules. How do I know I have a molecule? Okay, so said another way, whoops. Let's change that solid now to be what is the molecule? Okay. So who thinks they know where the molecule is in that compound? Damn it. So I made it too difficult. Okay. Who would like to hazard a guess as to where the molecule is in that compound? Okay. We got a volunteer. Middle, I'll accept that. So you're saying right there is the molecule. Okay. But right there isn't a molecule? And right there isn't a molecule. What is the problem with this substance? What kind of substance is it? A solution would imply another substance. Compound, can you name it for me?
Sodium chloride.
What's the symbol? If I ask you to give me the formula for sodium chloride. So I agree, you got awesome points for sodium chloride. What is the symbol?
NaCl.
NaCl, right? Not Na6, Cl6?
Well, according to the empirical formula.
An empirical formula, okay, so that's a good reference. Let's backtrack a little bit further. When can we use empirical formulas, or when are they best used? Right idea, wrong implementation. When are we allowed to use empirical formulas, or when is it best to use empirical formulas? Okay, and so you got, again, you're at the right concept level, but you're placing the wrong terms. Ionic compounds we don't use empirical formulas for, because we would never write Na6Cl6. We would only write NaCl.
Only covalent.
Empirical formulas make a lot more sense to use for covalent compounds. What is the issue with sodium chloride? It's an ionic compound. So that when I transition for the ionic compound from solid to liquid, what am I breaking? Well, I'm breaking each of the connections in between those. What are those connections? What kind of bond? Those are ionic bonds. How do you know they're ionic bonds? Say that? I think so. Not quite.
Because you have a metal and a non-metal.
Metal and a nonmetal is an ionic bond.
And then because it
Right.
ends in D, it's an ion.
And we can deal with it being as an ion with chloride. Okay, so more hints that it's an ionic compound. So if we look at it, what are the connections? Well, it could be an ionic bond. It could also be an ionic force. How do we really know? We don't. Okay, the ionic category in our ranking of attractions between molecules is a giant freaking gray area. Because depending on which side of that line we're on, we may call it bonds or forces. This is also one of the reasons when we talk about dissolving salt in water, classifying it as chemical or physical becomes difficult. Because if we classify the bond as ionic, well, when we break the bond, we're breaking a bond, that's a chemical change. If we classify that interaction as being a force, we're now breaking a force, that's not chemical. Okay? Because the connection is an ionic connection, and that's now why they're bonds or forces, depending on how I want to evaluate it, my definition of chemical versus physical changes becomes kind of a gray area. Okay? So when we're looking at our transitions between melting points or solids to liquids, it is going to be dependent on the attraction in between there. So when we look at that attraction here, it's an ionic something. That is either an exceptionally strong force or...
An exceptionally strong bond.
Is it an exceptionally strong bond? No, it's actually an exceptionally weak bond. Remember, our nonpolar covalent is the strongest attraction. London dispersion is the weakest. Okay? So our strength goes all the way around the circle. Okay? So it is either an exceptionally strong force because it's at the max end of the forces, or it's an exceptionally weak bond because it's at the bottom, effectively, of our bond interactions. Okay? So how do we go through and use that? Okay, well, that would be looking at our transition for the melting point for sodium chloride. Okay? What's breaking? So the argument that I would make here is that when we're looking at our phase transition, actually let's draw the next one. I changed my mind, sorry. What happens when I take ice and turn it into water? What am I now breaking? Okay. And so now if I went into water, I'm going to pretend that we now have shown more motion. Is everybody okay with that? That kind of makes sense? There's more motion now because I've changed their orientation. For the solid, that orientation is a pretty good orientation. Why is that orientation a pretty good orientation for the solid in water? You want a hint? I'm going to take that as a yes. We have these partial charges, right? Why is that orientation a particularly good orientation? That orientation brings what two things close to each other? Kira, you're nodding. Nobody else nodded.
Because it's the negative and positive.
I'm bringing that negative and positive near each other. That negative and positive allows those charges to balance out. Okay? So what we're saying is that there's an attraction between those. When I go through to make it liquid water, what did I do to the bonds?
You changed the charges to where now you have a partially negative close to a partially negative.
Okay? So you could make the argument, well, I changed the orientation of those, okay, which is perfectly valid, but that's also not the question I asked. The question I asked is, what did I do to the bonds? Okay? Well, to address that question, you would have to identify, what the hell's a bond? How do I know I have a bond? Isn't it just the little line between the two atoms? Yeah, Lewis structure. Okay, now shown in green. Those are my bonds in the solid. What happened to the bonds in the product? Okay, in the liquid. Nothing happened to them. So when I transition from solid to liquid, am I breaking bonds?
No.
No. Our physical properties are not dictated directly by the bond. They're dictated by the, I think I heard you mumble it, maybe not. Force? Did you say that? I was all the way down there? Okay. They're dictated by the force. So when we go through and evaluate the difference here, what is the force in our water molecule? Well, how would we determine that force? It's what we walked through on Monday. First, we have to identify what the bond is. What's the bond in water? Is it an ionic bond? James knows this one because he knows what an ionic bond is because he told me the definition. The definition for ionic bond was
Metal and a non-metal.
metal and a nonmetal. Is oxygen a metal?
No.
Is hydrogen a metal? No. Oh, no. Just because it's on that side, don't do that. Okay? Hydrogen is not a metal.
That's it. Yeah, that's good.
Okay? Is it an ionic bond?
No.
No. Is it a non-polar covalent bond? Okay? And I like where James is going. He's flipping back to his notes. Man, like I know I wrote down what those bonds were supposed to be. Okay? That's awesome. You should be doing that because you need to be able to look at that structure and be like, that is that bond. What is the bond between O and H? It's not ionic. Is it non-polar covalent? No. Why not? What is non-polar covalent? Not no charges.
Non-metal and a non-metal, the same element. And
Same element to same element, or
hydrogen to carbon.
carbon to hydrogen. Is the OH bond same to same? Is it carbon to hydrogen?
It's not a bond.
It is not a non-polar covalent bond. If it's not an ionic bond and it's not a non-polar covalent bond, then what is it?
Polar.
It's a polar covalent bond. So once I've classified the bond type, I can now match that to the force type that is associated with it, which is what we walked through again on Monday. Okay? That's what this diagram is attempting to show. If I have a green polar covalent bond, what kind of force does that result in? Well, a green force. What is a green force?
Dipole,
Dipole,
or
or hydrogen bonding. How do we know we have hydrogen bonding?
we must have a dipole to dipole with hydrogen.
You have hydrogen. Half right.
And it has to be linked to either fluorine, oxygen, or nitrogen.
It has to be connected to fluorine, oxygen, or nitrogen. Do we have a hydrogen?
Yes.
Yes. Is it connected to oxygen, nitrogen, or fluorine?
Yes.
Yes. What is our force? Hydrogen bonding. What was the force in the sodium chloride example?
Ionic.
Ionic. Which force is stronger? The ionic one. If it is a stronger force, what does that mean about the energy I have to put into it to break it? I have to put more energy in. How do I represent my energy? Someone was super active and moving around. Okay? Kind of like Greg. What would Greg look like at the end of class? Sorry, Greg. I'm going to throw you under the bus. He'd be. Why is he sweating? Because he got hot. How do we measure our energy? Temperature. So when we're looking at our solid to liquid phase transition, how do I know I've added enough heat to cause that ionic force to break? I would see it become a liquid. Because that force is a stronger force than water, what would I expect for the temperature to transition to solid to liquid for an ionic compound versus water?
It would be greater.
The ionic compound has a higher melting point. How do we determine that? All back to the intermolecular forces. Okay? It is this exact example that tends to mess people up. Okay? And people go through and say, well, ionic bonds are stronger bonds than nonpolar covalent. Why? Because their melting points are higher than covalent compounds. What dictates your melting point? Bond or force? It's the force. Okay? And it becomes tricky with ionic compounds because they're both a bond and a force on our classification. So when people try and think about using melting points or boiling points to predict things about the strength of those interactions and say, well, ionic bonds must be the strongest bonds because they have the highest melting points. They have the strongest force, which is why they have the highest melting points. When I go through to melt sodium chloride, I am breaking all of those ionic bonds. When I go through to melt water, what am I doing to the polar covalent bonds in water? Okay. Kind of color-coded, the polar covalent we showed is green, pointing to green lines within each of those compounds. I know there's a shit ton of colors up there. What happened to the green lines when we go from solid to liquid? Nothing. What happens to the chemical bond when we melt something? Nothing. Okay? What is breaking is the intermolecular forces. Those forces are dictated from the bonds, but we have to see that interrelationship. Okay? Where this comes out as a kind of big overall concept, okay? If I boil water, okay, can I just delete everything? Yeah? I might be able to get it. Oh, that didn't work. I might be able to get it. So here's a pot, okay, with water in it, and I add a bunch of heat. What happens to the liquid water? It boils and it turns into, that's my representation of a gas. What is the identity chemical formula for the liquid? H2O. What is the chemical identity for the gas? H2O. When I'm boiling this water, what do I see in the liquid water? I see bubbles. Okay, that's a bubble. What is in that bubble? What is the identity of the thing in that bubble? So I will accept gas, but gas isn't an identity, that's the phase. What is the identity of the thing in the gas?
H2O.
H2O. This question has been asked of graduate students. Roughly 50% of graduate students in chemistry will tell you that the identity of that bubble is hydrogen gas and oxygen gas. What did they say happened when we phase transitioned?
That there was a decomposition.
A chemical reaction where we physically broke chemical bonds. Is that happening in phase transitions? No. You've now had one semester of chemistry. You have already done better than 50% of the people that have been admitted to advanced chemistry degrees.
Well, calling it a day.
Yep. All right. This class is over.
Okay? That's pretty phenomenally cool. Okay? At least I find that really cool. Okay? That requires lots of processing of seeing all those intricate pieces and how they tie to each other and recognizing what is happening at each of those transitions. Okay? At a very base molecular level. Okay? That's pretty cool. So that's awesome for you. It is also insanely disturbing because what do those graduate students potentially go on to do? I'm going to stop recording that. Now that the official stuff is over. So, vapor pressure. Actually, because we got things that we could look at. Melting point and boiling point. So we just broke down some problems here. Okay, we're looking at now at potential questions. These are a lot more complicated than the ones we just looked at. Why?
They primarily have to do with the same chemicals.
Okay, well let's take a step further back. Okay, and let's do a review of what we just covered. Okay. And the moron that put this slide together, me, wasn't paying attention to the order in which they picked examples. They're in reverse order. Number 1's the hardest of these to figure out. 4 is the easiest. Okay? We just looked at the example sodium chloride versus water. Okay? And based off of that, we said the sodium chloride had ionic bonds. Because it has ionic bonds, it has ionic forces. Water, on the other hand, has polar covalent. Don't get them confused on the exam. Thank you. Polar covalent bonds, which leads to, okay, and I'm okay with you jumping to hydrogen bonding, kind of because it's water, but I would argue you shouldn't jump there right away. You should jump first to dipole-dipole. Because I have a dipole-dipole force, now I can consider, do I have hydrogen bonding? Do I have hydrogen bonding? Yes. Okay, and both of these are forces. How do I decide melting point or boiling point? Now that I know the forces that I can look at, I'm comparing ionic to hydrogen bonding. Which is the stronger force? Ionic is the stronger force. Because it is the stronger force, what does that mean about its melting point? The melting point must be higher. Okay? That's the work we just summarized. Okay, I use pictures and colors. I use less colors this time. 4. Why is 4 now more difficult than what we just went through and did? Yes.
Well, more than 2 elements in the...
You have more than 2 elements. Well, that's dumb. Dude, that's a pretty big thing to acknowledge. Right? You should acknowledge those differences and try to think about what's going on with it. When we look at sodium chloride and we look at water, both of those are relatively simple structures. We can draw those Lewis structures very quickly. How many of you can draw the Lewis structures for either 4A or 4B quickly? That face is exactly what I wanted to see. Okay? Not a lot of us can do that. Okay? Are you responsible for it? Yeah, it's kind of a big, massive gray area. I would argue no. The responsibility for drawing those Lewis structures happens ultimately in organic chemistry. You aren't there. Okay? It kind of shows up maybe in 151. So what do you then need to do? Okay, well, if we go back and look at the previous example, in the work that we showed up here, does everybody follow that work? Yeah. Did anybody see me draw the structure for sodium chloride or water in the work on this page?
No.
Do I need the structure? No. What do I need to do to answer this question between A and B?
Figure out the bonds.
Figure out the bonds. What are the bonds in those compounds? And vague question, don't classify yet. Just tell me what bonds you see. Okay? For instance, the bond I see in sodium chloride is NaCl. That's a bond.
So carbon to hydrogen.
Carbon to hydrogen.
Oxygen to hydrogen.
Oxygen to hydrogen. Does anybody see anything else? Okay, fair enough. What kind of bond is carbon to hydrogen?
It's non-polar.
Non-polar covalent. It's okay. You need practice. If you knew it already, you wouldn't be in the class. Why are you here again, James?
Because I need this class for my degree, apparently. It baffles me as to why.
What's the bond between the O and the H?
Polar.
It is a polar covalent bond. Once we know the bond, what do we move to?
The force.
What's the force between carbon and hydrogen? What's that going to generate?
It's the London dispersion.
That is our London dispersion force.
So wait, why is carbon and hydrogen non-polar, but oxygen and hydrogen is polar?
What is the difference between our polar and non-polar?
Well, I mean,
How do we come up with those classifications?
Oh, actually, I think I remember it because
Okay.
with non-polar, that it applies to the same 2 elements unless we have carbon and hydrogen.
Carbon and hydrogen, so it could be just the rule, but why that rule? How do we know they're ionic, polar covalent, or non-polar covalent?
If there's something is below,
If there's something
I
good,
forget what it's called.
What are you adding? What are you adding in?
Money.
Nothing? Okay.
No, one of them.
There's something, yes. There is a something. If there's something is below, if they're what?
That's the electronegativity.
Electronegativity. So in absolute electronegativity, there's two different elements. It's the difference in electronegativity. If their difference in electronegativity is below a certain threshold, now it's nonpolar covalent. If it's above a certain threshold, it's ionic. This is why same to same works, because same to same, what's the difference in electronegativity? Zero. That's why it's nonpolar. There's no polarity. There's no electrons shifting from one side to another. Okay? So that's why same to same. Why do we throw carbon to hydrogen in there? Okay? That threshold on where we decide that line is, okay? How do I know it's red versus orange on the rainbow? Does anybody see a nice solid line where it's that side's red, that side's orange?
No, it blends.
No, it blends. There's a giant freaking blending area. Okay? Ultimately, we just decided everything above that's red, everything below that's orange. Okay? There's no red orange. That doesn't exist. Okay? Not there. There's not sunset red. Okay? It's red and it's orange. The same thing's happening with our bonds. We decided a line. That line happens to include carbon to hydrogen difference in electronegativity being classified as nonpolar covalent. Why do we add that special rule for carbon and hydrogen?
Because their electronegativity is under that threshold. Right?
It's under that threshold, but why would we add that as a rule? Why not just say same to same and then deal with the electronegativities? Why carbon hydrogen?
Because if we didn't know that, then we just define that as polar covalent. Right?
What is the study of organic molecules about? What's the study of organic molecules about? Carbon, a little bit better. Carbon and hydrogen. What makes up all life as we know it? Carbon and hydrogen. Why are we classifying carbon and hydrogen as a special rule for our nonpolar covalent? Because damn it, that shows up in a lot of freaking places. It is such a common bond that we're going to have to work with it so much, we might as well establish a rule and memorize how that interaction plays out because we're going to see it so often. Okay? So that's why you're told to memorize that carbon and hydrogen one. There are plenty of other ones, right, that fall in that category. But how often do we see them? Not very often. So we don't bother to memorize the rarities. We bother to memorize the ones that we're going to be most often exposed to. Okay? Why is the oxygen to hydrogen polar covalent? Okay? Well, it's not same to same, and it's not carbon to hydrogen. Okay? Officially, the difference in electronegativity between those two is larger than the classification for nonpolar covalent. Also, officially, it's smaller than the classification for ionic. Right? If we have a polar covalent bond, what kind of force do we have? Dipole to dipole. If we have a dipole to dipole force, what should we try to evaluate? Do we have hydrogen bonding? Do we have a hydrogen physically, chemically connected to oxygen, nitrogen, or fluorine? Yes, so we have hydrogen bonding. We move over to the next compound. What are the bonds you see in the next compound?
Carbon to hydrogen.
Carbon to hydrogen.
Oxygen to sodium.
Oxygen to sodium. What kind of bond is carbon to hydrogen?
Nonpolar covalent.
Nonpolar covalent. Right away, what should you do? That's now irrelevant. Why is it irrelevant?
Because they're the same.
It shows up the same in both compounds. I don't need to evaluate it. Right? It's not going to differentiate my melting points and boiling points. That may turn out to be a lie, but at a first approximation, that works really well. Oxygen to sodium. How do you know that's an ionic bond?
Non-metal to metal.
Sorry. That's a non-metal to a metal. If we have an ionic bond, what's the force? An ionic force. I know that looks a bit dumb, but that's how we're doing it. Bless you. Which is the stronger force, ionic or hydrogen bonding? Ionic, which means that compound will have a higher melting point. There's my answer. Thank you. That was appreciated.
But actually, because on the play posit, I was like,
DJ Joey.
Yeah.
and then now it's like, oh.
Okay. Which means what? When I now do that, can you answer the other three?
More than likely.
More than likely. You should do that before class on Tuesday. Okay? What we'll do on Tuesday is if you have questions about, like, I couldn't figure that one out, we'll answer that. Okay? Then what we'll do is move into our phase transition diagrams. Okay, real quickly, we'll look at vapor pressure. Okay, we got to look at solubility. Oh man, acids and bases. Oh, equilibrium kinetics and all that fun stuff. I'm going to try and race through all of that on Jiminy Christmas. It just keeps going, doesn't it? Yep, it does. We're going to try and burn a lot of content on Tuesday so that we can open, and I understand that, oh my God, just stop talking. So that Thursday can become a review. Okay, so that we can double back and actually look at that content that's been giving you a hard time. Okay, that's what I would really like to have done. Okay, that means we're going to have to do a lot more stuff on Tuesday. We're going to pick up the pace to get through that. We'll probably carry into Thursday a little bit.